Good evening everyone. My name is Devanand. I am faculty of Heat Transfer in AC Engineering Academy, Hyderabad. So as the program is scheduled for TSPSC Polytechnic Lecturer, so the today's agenda is what are the important areas where you need to focus. So this is not for any other competitive examination like GATE and engineering services, that is different thing. This session is only for the Polytechnic Lecturer. Okay. Now, why I am saying like that? Because when it comes to other exams, GATE, public sectors or any other engineering services, their requirement is different. So the first step which is very important, that mode of exam, like how to prepare for that exam, that is our agenda. So my name is Devanand Gautre. So I will start today heat transfer important sessions. So our coursework is, I will discuss the questions, along with that I will try to give you the important concepts. Okay. So we will start. So let us take this question. This question. Now, if you see the question, what is written? Lump system analysis assumes a uniform temperature. Okay. Distribution throughout the body, which will be the case only when the thermal resistance of the body to the heat conduction is. So listen carefully. Here the very keyword is this one. So this is keyword, right? What is that? Lump. So lump case. Chalo. Now we will discuss this one. So everyone pay attention. Suppose if you take any body, here, right? Now what I am trying to say, let us say this is the temperature. This is the temperature when the heat is trying to penetrate. When the heat is trying to penetrate here, what will happen? The material will keep on offer resistance. So actually what we want here temperature. When the heat penetrate, I want here also same temperature. I want here also same temperature. I want here also same temperature. So let us assume if it is 50, I want here also 50, I want here also 50, I want here also 50. I want this one. I want this. But in reality, this not happens. Why? Because when the heat is trying to flow, material start offer resistance. So as a result, what happened? We are expected this one, but the drop is something like that. Then again drop is something like that. Drop is something like that. Drop is something like that. So temperature keep on dropping down. Why? Because there is a resistance for the heat flow. So that's why this here 50, everywhere 50 not possible. But if you ask me, sir, under what condition it is possible? So it is an imaginary case. So temperature is uniform. If you say like this, if you say like that, temperature is uniform, means everywhere it is same. Here. Everywhere it is same, then it is called lump body. Okay. So this is called lump body. So temperature is uniform. So if temperature is uniform everywhere, then it is considered as a lump body. So dear student, remember one thing. If everywhere temperature is same, this is called lump body. And this is the imaginary case, because for lump body, conductive resistance is 0. R conduction is equal to 0. Conduction resistance 0. So this is purely imaginary case. Because if you want everywhere temperature is same, then it is only possible when the resistance is 0. So in this case, what options you will pick? So for that you will pick 0. This is the option you will pick, right? So that is the question. So what do you mean by lump body? Remember one thing. Lump body means, remember, let us say this is the time equal to 0. Right now it is here 50. Assume that everywhere it is 50. Assume that everywhere it is 50. Now when the body start cool down, what will happen? This is 50, but this will be 30, this will be 48, this will be 47, this will be 46. Like that it happens in reality. In reality, the center will be hot and other side will be cool. So this is your real body. So this is real. But suppose if I assume, no sir, imagine that everywhere it is same. So 40, 40, 40, 40, 40. If you assume everywhere same, then it is called lump body. Then it is called lump body. So in case of lump body, everywhere temperature is same, and this is only possible when the resistance is 0. When the resistance is 0. That's why we need to go for this option 0. Hope it is clear. Now, next question. Next question. Which one of the following is not a fluid property? Okay, so he is saying that which is not a property. Okay, so this is very important, not a fluid property. Not a fluid property. So now, dynamic viscosity mu. Mu is a property, K is a property, density, these are also property. So if you are not sure about the rate of convection, then leave it. Dynamic viscosity, property, thermal conductivity, property, density, property. Rate of convection means he is talking about heat transfer coefficient. So this he is talking about heat transfer coefficient or rate of convection. So heat transfer coefficient he is talking about. Okay, so why it is not property? Why it is not property? Try to understand. This is the plate, and let us say this is the hot plate. This is the hot plate, and let us say there is a fluid from here. There is a fluid from here, T infinity. Why it is not fluid property? Please listen carefully. Suppose if this plate having some roughness, let us say this type of roughness is there, and let us say this side is smoothness. So this is smooth, okay, and this is rough. This is rough. So this one is a rough, this one is a smooth. Now when the fluid is flowing, when the fluid is flowing, there is something called convection. So there is something called convection. Convection is there. Now when the fluid is contact with the smooth surface, its flow pattern is different. Its flow pattern is different, and when the fluid contact with the rough surface, flow pattern is different. When there is a roughness, there is a suddenly turbulence will generate, and the layer by layer will mix each other, and that will enhance the heat transfer. So here the heat transfer is different, here the heat transfer is different. Rate of convection means convection heat transfer with respect to time cannot be property, because it is not only depend on fluid, it is also depend on the surface conditions. Surface is rough or smooth, that's what. So that's what this cannot be called as property. Okay, so in this you should go for D. In this case you should go for D. So that cannot be called as fluid properties, right? So this is smooth, this is rough. Hope it is clear. Very simple question. Dynamic viscosity, thermal conductivity, density, rate of convection, right? Next next question. It is design of a fin. The error involved in the one-dimensional fin analysis is negligible. Now try to understand. Let us say this is the fin. Okay, this is the fin. Okay, now this is your thickness. So this is your thickness delta. This is your thickness delta. Now you try to understand. Let us say it is 100, and let us say it is 80, and let us say it is 70. Suppose this is the case, that there is 100 and there is 80, and above there is a 70. Now what I am trying to say, in this direction also heat will flow. In this direction also heat will flow. In this direction also heat will flow. As you can see, in both the side heat will go. Why? Because 100 minus 80 heat will flow, 100 minus 70 heat will flow. In both the side heat will flow, right? So heat will flow in the both sides, right? Now the question is, sir, what to do then? I don't want two-dimensional, because I don't want to use the multiple lengthy equation. I want to make it in a very simple way. So I want to make it. So what I will do, this is the, I make it thin. I reduce this delta. So what will happen? Here it is 100. Let us say here it is 100. Here it is 80. So the thickness is so small, thickness is so small that it is very thin, ki the center and the surface almost same. Center and the surface, there is no much temperature drop, so that's why the heat will go only in this direction. So this direction we can neglect. Why? Because center and the surface almost same, so let us say this is 99.99 in upward direction. In this direction, let us say 199.99. So this will be flow. Okay, this will be the flow. So what does it mean? This should be small. This should be small, correct or not? This should be small. So delta should be small for 1D. For 1D. Okay, next. Delta should be small for 1D. Next, if it is a fin material means it should be good conductor of heat. So K should be high. K should be high, correct or not? Because if you call it as fin material, fin should conduct the heat. So K should be high, and now H should be less. Heat transfer coefficient should be less, because if the heat transfer coefficient is less, then only we can use the fin. Otherwise, we will not use the fin. So what I am trying to say, H should be less, okay, K should be high, and for the one dimensional, delta should be less. So if you rearrange this, H delta by K, so this should be small. This should be small. This should be small. So H should be small, delta should be small, K should be small. So in that case, you can see, K should not be on numerator. If the K is in numerator, the K will be high. So K should not be in numerator. So K should not be in numerator. Otherwise, K value is high. This should not be the option. Remember H delta T by K. So this should not be 2. It is large value. So this is the right answer. This is the right answer. So H delta by K should be less than 0.2. Okay, less than 0.2. This is the mathematical condition. Standard condition, H delta by K should be less than 0.2. In order to take that, it is a one dimensional, okay. So K should be high, H should be less, delta should be less. So this is the condition. Okay, next. Next, this is the question from convection. This is the question from convection. What you can say? What is the traditional expression for calculation of heat transfer in fully developed turbulent flow? What is the traditional expression for calculation of heat transfer in fully developed turbulent flow in smooth tubes that recommended by Dittus-Boelter? Okay, so Dittus-Boelter. This is the equation used for turbulent flow, okay? So this is for turbulent flow. This is for turbulent flow. Now what you can write? You can write Nu base upon diameter 0.023, Reynolds number raised to power 0.8, Prandtl number raised to power n. So this is your actual equation. This is your actual equation, and this n is equal to 0.3 for cooling, 0.3 for cooling, and n is equal to 0.4 for heating. Okay, 0.3 for cooling, and this is 0.4 for heating. So this was the case. So here always remember, sometime what happened, sometime the same expression written like that, 0.023 Re raised to power 4 by 5, Prandtl number raised to power n. So sometime 4 by 5. Here it is 0.8 is there. So you can go, what you will get? NUD is equal to 0.023 Re raised to power 0.8. Yes. So now Re raised to power 0.4 not correct. Re raised to power 0.4 not correct. Now remaining it is 0.4, 0.4. Now 0.4 cancel, 0.8, 0.8. Now make sure that it should be only n. It should not be 2n. It should not be 2n. So this is your answer. So A should be the answer. A should be the answer. Okay. A should be the answer, right? So n is equal to 0.3 for cooling, n is equal to 0.4 for heating. So this is Dittus-Boelter equation, right? Make sure that, remember, if it is laminar flow, this equation cannot be used. If it is a laminar flow, this equation cannot be used. This equation only valid for a turbulent flow. Valid for turbulent flow. Okay. Now, next. Listen here. Listen. What is the critical radius of insulation for the asbestos, thermal conductivity, surrounding circular pipe exposed to room, 20 degrees Celsius, heat transfer coefficient. So there is a pipe, everyone pay attention. So this is the pipe, we are insulating. So let us say this is insulation. This is K of insulation, right? So K of insulation is equal to 0.17 watt per meter Celsius. Watt per meter degree Celsius. This is the K value given. Surrounding exposed to room at a temperature, heat transfer coefficient. So H of outside, how much it is? How much it is? That is 3 watt per meter square degree Celsius. So this is the condition given. Now please listen carefully. Here it is a K of insulation. Here it is a K of insulation, right? Right. Now for cylinder, what is RC formula? So for cylinder, okay, for cylinder, what is RC formula? RC formula is equal to K insulation by H outer. So this is the formula. But once again you have to read the question. Once again you have to read the question, and if you read the question, what he asked, he did not ask critical thickness. He did not ask critical thickness. He asked critical radius. So this is the formula. So K insulation is equal to 0.17 by 3. Okay, 0.17 by 3. So this value, if you substitute, check, it is watt per meter, it is also there. So if you solve this, so you will get around 5.67 centimeter. If you solve like this, so you will get around 5.67 centimeter. Okay, so this was the answer. This was the answer in centimeter. But suppose if he asks thickness. So if he asks thickness, so thickness is different. In this problem, he asks only RC. So he has critical radius of insulation. So always remember, see, this is the graph. This is the graph. Okay, this is your RC. Okay, and this is your Q max. This is your Q max. Okay, so what happened when you insulate up to RC? Let us say this is your radius of insulation. Let us say this is your radius of insulation. If this radius of insulation, if you are insulating, initially what happened? Initially heat loss will increase. Initially heat loss will increase, right? So heat loss will increase, and beyond that it will decrease. So what is the critical radius here? The critical radius is something like 5.67 centimeters it is coming, right? So something, right? So this is the answer is coming. So this is the radius at which your heat loss is maximum. So what is RC? RC is critical radius at which heat loss is maximum. Heat loss is maximum. So listen carefully. RC is a critical radius at which heat loss is maximum. So maximum heat loss. So this is your RC. Now if the same question asks for sphere, what you can write? For sphere. If I ask you what is for RC for sphere, then you will say RC is equal to 2K insulation by H outside. So this is the formula for sphere. This is the formula for sphere, and this is the formula for cylinder, right? So this is the case. This one is the case. So listen carefully. Here he asks RC, not the thickness. Hope it is clear. Now move to the next question. Here, next question. The purpose of providing fin on the heat transfer surface. So let us discuss this one. Let us imagine this is your IC engine. Let us discuss this case. There is a IC engine, and in that IC engine there is a continuously combustion. Okay, so let us say there is a continuously combustion, right? If there is a combustion, right, now what will happen? This surface get heated. So this one, this color I am using for color, so this will get heated. Okay, now what is the purpose? Here in the engine there is a continuously combustion. Continuously there is a combustion. Because of that combustion, entire IC engine get heated. It is heated. Now we need to cool. So the purpose is we need to cool the engine. Cool the engine. Cool the engine. So if you see Newton's law of cooling, what does it say? Ki H as Ts minus T infinity. Ts minus T infinity, that is Newton's law of cooling. So I want to increase this heat loss from this point. So you want to increase Q convection. You want to increase Q convection, right? So if this is Q convection, what is the first point? First point is you need to increase H. You need to increase H. What is H? H is a heat transfer coefficient. How to increase? How to increase? You need to attach fans here. So listen carefully. There is a fans. Now you need to attach fans here. Okay. Suppose if you attach fans here, then what will happen? This body will get cooled down. So the option number 1, whenever you feel hot, what you will do? You will switch on the fan. So increasing the velocity increases the H value. So this will increase. Second option, you need to reduce the outside temperature. So whatever outside temperature is there, that has to be reduced. So let us say this one, T infinity, need to be reduced. T infinity need to be reduced. Imagine that it's a winter. In winter, outside conditions are very low. So of course we feel comfortable because from our body there is a heat loss continuously. Okay, it should not be below level in winter. But here I need to cool the engine. So if I want to cool the engine, that ambient temperature need to be reduced. So option 2. And third option is there, this one. So what is third option? The third option you have, you need to increase surface area. You need to increase surface area. So increasing surface area. Now example. Let us say we will drink this tea every day in a cup. Okay? In a cup we will drink every day. But suppose if the same tea here, same tea on this saucer. Okay, if you put it on saucer, there is a more area. So because of that, this tea will rapidly get cooled down. Okay, this will get cooled down if there is a more area. Of course, when it is in cup, area is very small. When it is in cup, area is very small. Here, area is large. So there is a rapid heat loss. So increasing area also one of the choice. Now what I am trying to say, if you don't see ambient temperature outside we cannot reduce. Let us say there is an environment temperature we cannot reduce. So in decreasing temperature is not at all choice. So this will get cancelled out. Next option you have, increase the H value. What is the option you have? Increasing H value. Higher the H means you need to install the fans. Fans will take noise, fan will increase the cost, fan will increase the other maintenance issues. So if you are ready for that, to take care of higher H, if you are bear the electricity bill, if you bear the noise, and if you are ready for installation of fan, then your problem solved. But what happened? Increasing or attaching fan is not possible in every case. There should be electric supply. There should be a proper arrangement. That's why if this is not in your control, then you have only one option, that is increasing area. So please listen, in the previous problem what I said, we will attach the fin when H is less. So if the H is not high, and we don't want to increase or it is not increasing, if it is not increasing, then you have only one option, that is surface area. This you have to take care. Then you have only one option, that is surface area. And if we attach the surface area to these fins, just we are increasing, right? If we attach these fins, right, in order to increase the area, then what will happen? Heat loss will increase. So this extra attachment is called fins. This is called fins. So fins are the extra area. So if you read the question, what you can say? The purpose of providing fins on heat transfer surface area is temperature gradient so as to increase the heat transfer by convection. No, it's not because of temperature gradient. Next, effective surface area to promote the rate of heat transfer by convection. Very good. Turbulence in the flow for the enhancing heat transfer by convection. No. Pressure drop of the fluid. No. Among all the options, where we can pick effective surface area to promote rate of heat transfer by convection. So that was the choice. Effective surface area to promote the rate of heat transfer by convection. So what is fins? Fins is the extra area attached. Fins is the extra area attached in order to increase the heat transfer rate by convection. When H is not increasing. If the H increase, why we need fins? We don't need fins. Okay, so that's what the case. Next. Next point. Listen carefully. This is from radiation. A hemispherical furnace of a radius 1 meter has a roof temperature of T1 800 Kelvin and emissivity 0.8. The flat floor of the furnace has a temperature 600 Kelvin, emissivity 0.5, the view factor F12 from surface 1 to 2. Okay. Listen, this is the hemispherical furnace. So I will change the color. Let us say this is the hemispherical furnace. This is visible. Okay. Now, listen, this is roof and this is floor. Numbering, this is 1 and this is 2 given. Now we need to calculate view factor. View factor also called as shape factor. So what you need to do, separate this figure. So it's a hemisphere. So it's a hemisphere. Okay. This is the hemisphere. Now, what is the bottom? Bottom, even though he used the word flat, but what is the shape of the flat? It may be rectangle or it may be circle or it may be sphere. Depends. It is a hemisphere above. If it is a hemisphere above, this will be a circular plate. Correct? This will be circular plate. So this is the flat plate, right? This will be the flat plate. Okay. This will be the flat plate. Radiate like this. And this will be the hemispherical dome, radiate like this. Okay, this will be radiate like this. Now you can see this radiation, in this case, it is going to strike with itself. So in this case, what you can say, F11 not equal to 0. It is going to strike with itself. Correct? It is going to strike with itself. Then apply summation rule, F11 plus F12 is equal to 1. This is 0, this is not equal to 0. Okay, this is not equal to 0. Right. So what you can say, not equal to 0. Now here, what you can see, it is a flat surface. So it will not strike with itself. So F22 is equal to 0. Everything will come outside. It is not going to strike. See, this is the flat plate, everything going outside. Right. So what you can write, this is the radius R. So F21 summation rule, F22 is equal to 1. This is 0. So F21 is equal to 1. What does it mean? Whatever the 2 radiate, everything will fall on 1. Okay, that's the logic. Now here, what is A1? Area of hemisphere. Area of hemisphere is 2 pi r square. What is radius given? 1 meter. So you can substitute. What you will get? You will get it is 2 pi. You will get it is 2 pi. And here it is A2. A2 is equal to circle area pi r square. So A2 is equal to, you will get pi. And here you will get 2 pi. Chalo. Right? Now, apply reciprocity rule. If you apply reciprocity rule, what he said? A1 F12 is equal to A2 F21. Right? This is reciprocity rule. Now F21 is 1. So what he asked? F1 to 2. So F1 to 2 he asked. So we will write A2 by A1 into 1. So F12 is equal to, what is A2? That is pi by 2 pi, and this will be, okay, right? Now this is into 1. So this get cancelled out, you will get 1 by 2, and that is 0.5. So F12 is equal to 0.5, right? Shape factor. So any options are there? Yes. 0.3, 0.4, 0.5. So C is a right answer. C is a right answer. Like that, for many other geometries you can solve this. For the many geometry you can solve this, right? So this is the shape factor. So what I am trying to say, listen, what I am trying to say, first you have to visualize. See, nowhere it is mentioned that ki base is circle, right? He just said that flat. But you need to understand if it is a hemispherical dome. If it is a hemispherical dome, let us say lemon, and if you cut it the lemon from middle, so above one will be the hemisphere. So what is the base? Base is circular plate. If you cut the lemon by half, you will understand this, right? So exactly the same thing here. They will not say what is the shape. You have to understand. This is hemisphere and this is your base, circle. So if you do that, you will get this one, that is 0.5. You will get 0.5, right? This is the question from radiation. Next one. A wire of diameter 4 means diameter 4 mm. Okay. So again I need to change color. So let us say there is a wire. Okay, this is the wire. Diameter 4. So radius is R is equal to 4 mm. Let us say R1, 4 mm. At a temperature 60, okay, is to be insulated. Okay, so let us say there is a insulation. This material having insulation, K insulation is equal to what? 0.17 watt per meter Kelvin. Heat transfer coefficient on the outside. So let us say outside, how much it is? 8 watt per meter square Kelvin. The ambient temperature 25. The maximum thickness of insulation for the heat loss. So he said that what is the maximum thickness? First you try to understand. For maximum heat loss, R radius of insulation should be is equal to RC. Means you need to insulate up to RC. For maximum heat loss, you need to insulate up to RC. And this is the wire. So for cylinder, what you can write? RC is equal to K insulation by H outer. So RC is equal to K insulation given, that is 0.17 by 8. This is your RC. You will get it in mm. Right? Now you will get it in mm. Now okay, but this should not be the answer. Why? Because if you read the question, what he asked, the maximum thickness of insulation. So he asked for the thickness. So what you can write? Thickness of insulation. So this is thickness of insulation. So what is thickness of insulation? That is RC minus R1. So what should be the thickness for maximum heat loss? For maximum heat loss, your R should be RC. This up to RC you have to insulate minus original one. So what you can say, if you do that, RC minus R1, if you do that, okay. Now if you do that, you will get this answer, 17.75 mm. This is your answer. So 17.75 is your answer. But remember, RC is different. RC is around 21 point something you will get, so around in that. We are subtracting by 4. Diameter is 8. We are subtracting 4. So if you do that, you will get something like 17.75 mm is your answer. That is your answer, right? So that is your thickness of insulation. So please be careful. In critical thickness, you have to understand whether he asks critical radius or critical thickness. Thickness means RC minus R. Critical radius means only RC value. Most of the time student will get confused. They are unable to understand whether it is thickness or radius. Okay. So please make sure that this type of questions are very common. Next one. This question from convection. In liquid metals, thermal boundary layer develop much faster than velocity boundary layer due to, try to understand. First, always remember there is something called Prandtl number. What is Prandtl number? Prandtl number is nothing but kinematic viscosity kinematic viscosity by thermal diffusivity. Kinematic viscosity by thermal diffusivity. Okay, right? So it is something like nu by alpha, and kinematic viscosity, it's something like kinematic viscosity is something like, this is related to delta, this is related to del T. So wherever I am writing del T, T stand for thermal, so del T is your thermal boundary layer. Now what is liquid metals? What is liquid metals? Like liquid metals are like liquid mercury, sodium, liquid sodium, something like that. So example is liquid mercury. Our mercury, a very common manometric fluid or something like that. So what happened in that liquid metals, there are something called free electrons. So something called free electrons. In case of liquid mercury like that, it is called as free electrons. We have free electrons, and because of that thermal conductivity is highest. So K is high. In this case K is high. Now what is alpha? Alpha is equal to K by rho C. If your K is high, then alpha will be high. So alpha is dominating. So for liquid metals, alpha is greater than kinematic viscosity. So if you substitute here, then Prandtl number is less than 1, correct? Less than 1. So Prandtl number is less than 1 because this is the fluid where more heat transfer takes place. Heat transfer is faster. So Prandtl number is 1. If you go with this formula, what you can understand, delta less than del T. Sorry, here what you can say, Prandtl number less than 1, so delta less than del T, correct only, or you can say del T greater than delta. Del T greater than delta means, let us say this is the plate, if see up to this much heat is penetrated, so up to this distance there is a del T, and here is a small distance, that is delta only. So this is the del T and this is delta only. This is del T and this is del. So what is the question here? In a liquid metals, thermal boundary layer develop much faster than velocity. So you can see at a particular distance, here thermal is fast, so heat is penetrated up to here faster, and the velocity is only up to here. So del T is greater than delta, reason Prandtl number is low. First of all, try to understand, we will give this relationship between delta and delta T. This relation given by Prandtl number only. So Prandtl number will give relation of this. So here what you can write, what you can say, in liquid metals thermal boundary layer develop much faster than velocity boundary layer. Why? Because it is not due to Nusselt number. No Nusselt number. Nusselt number nothing to do here. So here what you can say, higher Prandtl number? No, it is a liquid metals. So in case of liquid metals, the Prandtl number is low. So this is your answer. In liquid metals, thermal boundary layer develop much faster than velocity boundary layer due to this one. See, lower value of Prandtl number. So this is your solution. Okay, next one. If you go to the next question, this is from again radiation. The temperature of the body of area 0.1 at 900. So let us say this is the body, temperature is 900 K. The wavelength for maximum monochromatic emissive power. So he is asking that what is that wavelength? For maximum monochromatic emissive power? Please listen. In this case, we will go for Wien's displacement law. Okay. So we are going for Wien's displacement law. What is Wien's displacement law? Wien's displacement law said that lambda max or lambda T is equal to constant, that is C3. What is C3? C3 is 2898 micrometer. C3 is 2898 micrometer. Okay, or closely also you can say near to 2900, okay, micrometer, roughly like this. Now, what is this lambda max? Lambda max is a wavelength. Lambda max is a wavelength at which emissive power is maximum. Power is maximum. Okay, so lambda max is a wavelength at which emissive power is maximum. So this is the relation. So what you can write, lambda max is equal to, you can write C3 by T. C3 is 2898 divided by 900, or you can write like that, roughly 2900 roughly by 900. Okay, so 900. So in this case, this 0 get cancel out, 29, so 3 point something you will get, 3 point something you will get. So here what you can write, here you can write, listen, here you can write lambda max is roughly around 3.2 micrometer something. So this one. So here what is the answer? Here you have answer of 3.2 micrometer. 3.2 micrometer. So this is your answer. So wind displacement law. What that wind displacement law said? Wind displacement law said that lambda max into T is equal to constant. So remember one thing, instead of this 900, if you put 1000, then it will be 2.98, 2.89 something. If you keep on increasing the temperature, wavelength will keep on decreasing. So here you will get the relation of lambda is inversely proportional to temperature. So this relation you will get, lambda, higher the temperature, okay, shorter the wavelength. So as you keep on increasing the temperature, then wavelength keep on decreasing. So this is the case. So please pay attention. This is your wind displacement law. So in that case, you can find 3.2 micrometer. So what I am trying to say, you will get the, in Polytechnic exam, you will get the very basic questions. Strictly speaking, no need to follow any gate questions or like that. No need to follow any particular gate. If you ask me, sir, what to follow, more relevant to your engineering services questions. So if you want to prepare, then go for engineering services paper, prelims, not mains. So in the prelims, whatever the questions are there, that is considered as a good question for the Polytechnic lecturer exams. Okay. So no need to go much detail. You don't require much fundamentals. If you have basic understanding of the heat transfer, normal formulae, in that critical thickness, wind displacement law, Stephen-Boltzmann law, plane wall resistance means what, like that. What do you mean by lumbar? Why I show you some basic questions. So in this session, I can't say that I covered everything. In this section, I can't say that I covered everything. I just given the glimpse of that. What is going to happen. Most of the questions are memory based, some memory based, superficial knowledge required. So no need to go in much detail. Whatever I covered, this is just a brief view of that. So what I'm trying to say, go for previous engineering services, download the papers or purchase the ACE Academy booklets, engineering services. In that, heat transfer is there in the paper one, you can go with that. So previous year engineering services question will be very relevant to your exam compared to either GATE. In GATE, detail and deep numerical calculations are there, that is not required. So this is from my side. I solved some questions and many things are there. Try to understand, many things are there. I cannot go in detail because heat transfer course itself a lengthy course. So I given the glimpse, this is like that. So prepare the notes and weightage is there, heat transfer weightage is there, but you cannot expect the many questions like other subjects are there like thermodynamics, fluid mechanics, strength of material. You don't find, compared to that weightage is less, heat transfer weightage is less, but you need to understand syllabus also late. We have only conduction, convection, heat exchanger, radiation is a part of syllabus, right? So you don't need to panic much more. So this subject will not make you the rank one, like it has more, don't have so much weightage, but okay, fair, nearly good questions you can expect, and with a very less time you can prepare that. So that's it from my side. Hope you understand what I'm trying to say. I cannot cover entire thing in a given limited of time. So I given the glimpse of that. Go to the fundamentals superficially and practice the engineering services. That's it. So this is from my side. Hope you understand, and wish you all the best for your upcoming exam.